Good morning, everyone. I'm Wei Jiaxu, and I'm the research director for the Good System Smart Cities, and I'm the group manager for Scalable Computational Intelligence Group at TAG. The Good System is a UT Grant Challenge and with a mission to developing human AI partnership that can benefit societies. The smart city technologies have great potential to contributing to these missions. To advance our knowledge and facilitating research around smart cities, and we started sliding presentations every Tuesday morning from 10 to 10:30. Today, we are delighted to feature the work of Dr. Bo Zhou. Dr. Zhou is an associate professor in the Department of Civil and Materials Engineering at the University of Illinois at Chicago. He is also a faculty partner for the Center of Excellence of Airport Technology at the University of Illinois at Urbana-Champaign. He is the director of the Translog Lab and with a focus of the evolution of mobility system driven by technologies. We're excited to host Professor Zhou's presentation today on predictive modeling for online shopping today. Dr. Zhou, thank you very much. It's all yours.
Thank you very much, Wenjia, and thank you for inviting me to this seminar. So I hope this will be more interactive and less formal. So feel free to interrupt me if you have any question. I'm going to share my presentation slides. So as Wenjia said, my name is Bo Zhou. I'm an associate professor in Civil Materials and Environmental Engineering departments at the University of Illinois, Chicago. My research is mainly in transportation systems analysis and modeling with a recent focus on emerging technologies, including autonomous vehicles, crowdsourced urban delivery, urban air mobility, and other types of technologies and impact on transportation systems. So today I'm going to talk about more on the transportation demand aspects, modeling the household online shopping demand in the US using a kind of machine learning approach, and comparing the online shopping demand change between 2 years, 2009 and 2017, using two latest versions of the National Household Travel Survey data. So this research was supported in partially by National Science Foundation and by the Department of Energy. I would like to acknowledge my collaborators, Limon Arua, who is a PhD candidate, my students at the University of Illinois, Chicago, Dr. Joanne Zhou, who is working at Oregon National Lab, and Dr. Yulin Liu, who was formerly at UC Berkeley and now working as data scientist at Amazon. So the research I'm presenting today is based on a paper which is under review in transportation. So the background for this topic, why we're interested in online shopping demands, because it's rapidly growing. Online shopping transaction in the US increased from just between 2018 and 2019, increased from $524 billion to $600 billion. And the growth has been further accelerated because of the still ongoing pandemic. There are some profound impacts of this online shopping demand growth. First, there's online shopping may substitute, complement, or modify personal travel to stores. This has been already studied by many researchers. There's also increase in truck, van traffic for goods deliveries, which raise many concerns such as road traffic congestion, shortage of freight, parking space, aggravated road wear and tear, among other negative impacts. The freight demand derived from online shopping exerts increasing influence on planning and operation of transportation systems. Therefore, the ability to predict e-shopping demand is important to design ways to manage, to maintain and enhance performance of freight and overall transportation systems. Understanding the importance of input variables in predicting and the nature of the dependence of e-shopping on the input variables is also critical to inform transportation planning and policymaking. We look at what has been already done in the literature. We find that predicting online shopping volume with reasonable accuracy has not been attracted much attention. The existing literature focused mainly on the interactive relationship between online and in-store shopping. Almost all existing works resorted to econometric statistical models, which may not be the most appropriate for prediction given the relatively low reported goodness of fit results. Most of prior research used small and local data samples. The broader understanding of online shopping demand at a national scale is still limited, and the two recent releases of National Household Travel Survey will help us overcome this issue. And thirdly, modeling online shopping demand from households' perspective is lacking. Existing research mainly look at individual level e-shopping behavior, but a household level may be more appropriate because some of the shopping purchases are not just for individual use, but for the entire household, such as grocery shopping. The empirical contributions of this work is as follows. We developed a machine learning models for predicting household level e-shopping demand using 2009 and 2017 US National Household Travel Survey data. We employ a gradient boosting machine, among other machine learning models. We have incorporated the various socioeconomic trip and land use characteristics and internet use of household members as input variables and look at their significance and impacts on online shopping demand. The results are compared between the 2 years during which e-shopping has experienced an unprecedented growth. The results can shed light on the changes and trends of factors influencing household e-shopping demand. In the paper, we also did some city-specific modeling for three of the 4 largest cities in the US, New York, LA, and Houston. But I guess for the interest of time, I'm not going to talk about this, but I can send you the paper if you're interested. From the methodological perspective, we use kind of 2 recently developed techniques. One is called Shapley value to quantify the input variable importance. The state of the practice for variable importance is based on Gini importance, which is known to be biased towards input variables with high cardinality. We also use a technique called the cumulative local effects to characterize relationships between response and input variables, which explicitly accounts for the presence of any potential correlation of input variables. GBM is a supervised machine learning technique that repeatedly feeds a weight classifier, typically a decision tree, and assembles the trees to make the final prediction. It has several strengths. First, it works well with high-dimensional mixed type inputs of numerical and categorical variables. Its performance is invariant to transformations of input variables and insensitive to outliers. The selection of input variables can also be internalized in the decision tree, making the algorithm robust to irrelevant input variables. In addition, GBM can handle complex correlated variables. From the National Household Travel Survey data, we initially came up with a pool of 45 input variables. Then we performed the recursive feature elimination approach to reduce the number of variables to 16 most relevant variables. And the table here shows these variables. As I said, the response variable is a number of purchases online by a household over the past 30 years from the survey dates. And we have 4 categories of the features: socioeconomic characteristics, such as household member age, percentage of males in the household, household size, income, etc. We have trip characteristics, such as number of trips per day, travel time, gas price, shopping trip percentage, the land use variables, and variable characterizing the internet use. As I said, we try different models. Besides gradient boosting machine, we have a random forest support vector machine and linear and nonlinear regression models. So here is just a table showing the goodness of fit results. We find that GBM performs the best and much better than just running regression for prediction. We specifically interested in the feature importance. As I said before, we use Shapley values, which is to overcome the drawback of the Gini-based importance that can be biased towards variables high cardinality. The Shapley values can fairly allocate a collision's output among members in a collision. In our context, collision members are input variables. Shapley values can characterize the member or input variable's contribution as an average value of every possible sequence of the input variables inputting into the model. So we calculate the inputs importance for the 2 years. On the left, it shows the value of the Shapley values. On the right-hand side, we plot the change in the ranking of the feature importance. We can see that in both years, household income is almost the most significant. On the other hand, daily internet use and percentage of male percentage, the second and the third most important variables in 2009, but they have their importance have declined. Average member age and the household size become the second and the third most important variables in 2017. In addition to knowing the importance of feature, we also want to know how the predicted online purchase is affected by the value of input feature. To that end, we use a cumulative local effects. The state-of-the-art method is called the partial dependence plots, but it can become unreliable when input variables are correlated. So the AOE technique is to overcome this issue. The basic idea is that for given input variable, we divide the value range of the observations into a given number, k number of intervals. And then there's some mathematical notations, but I'm going to just give you the general idea. We first calculate the difference of the predicted response value for a given observation for that input variable. When that input variable takes the upper and lower bounds of the interval. And then we average the incremental effects for that input variable, changing from the lower bound to the upper bound for all observations in that interval. And finally, we sum the incremental effects over all intervals up to the interval to which that specific observation falls into to obtain these accumulated local effects. Applying these cumulative local effects, we look at the relationship between online purchases with these various features. First, we look at the relationships with household income and member age. The top right figure shows a positive relationship between household income and online purchases, because when the household has a higher income, it means greater purchasing power, higher time value, and less sensitivity of the household to additional cost of shopping when shopping online, cost of shipping when shopping online. We observe a negative relationship between average household member age and online purchases. This is because young people have more computer skills and they have more positive attitudes towards using new technologies. By contrast, senior households, people perceive internet with greater risks and place more importance on the perception of self-efficacy in this context, shopping without relying on internet. In terms of the relationships with household size, we find generally increasing relationship, but when the household size is small, the online purchase is almost invariant in 2009. Also in 2017, the online purchases are much higher, so which means e-shopping has gained greater popularity. In terms of the relationship with the vehicle ownership, online purchases tend to be invariant to the number of vehicles in household, up to 4 vehicles in both years. 4 vehicles in 2009 and 2 in 2017. Most households in the internet have no more than 4 vehicles, as we found. And online purchases are not sensitive to households' vehicle ownership. Beyond 4, we observe a positive relationship. Our conjecture is as follows: these households could be engaged in vehicle-related businesses such as second-hand car sale, auto lease, or rental. These vehicles are typically not used for shopping. With large vehicle fleet to handle, households may have a constant time for in-store shopping. The message from the education variables is mixed. First, we find no clear trend for the impact of household members with a bachelor's degree. This is in line with the existing research. On the one hand, higher education leads to greater internet use capability, as found in some research. On the other hand, e-shopping is a relatively easy task and may not necessarily require a college education. But we still confirm that some basic education, such as high school degree, which means basic internet literacy is still needed, as shown on the lower left figure in terms of the percentage of household members without a high school degree. In terms of the adulthood in 2009, online purchases decreased with the percentage of adults in a household. At the time, non-adults, especially teenagers, might be more familiar with online shopping than adults. In 2017, those internet-versed teenagers had grown up as adults, leading to change in the trend. So in the very end, when the households has 80% to 100% adults, we find a declining trend. This is because households may consist of mostly senior and retired members who are more traditional and still go to stores for shopping. We also find that owning home property tends to encourage online purchase because this ownership gives household a sense of permanency and possibly more space. And this difference between owning and not owning a property is even greater in 2017. With chip characteristics, we find online purchases in 2009 first decreased and stay constant, then increase with gas price. The initial decrease seems a little counterintuitive. A possible explanation is that as gas price increases, the dominant factor may be reduction in allocatable budget for shopping. In 2017, online purchases are less sensitive to gas price, and also gas price fluctuated less in that year. As a household spends more time traveling, it is likely to have less time available for shopping. So we find e-shopping requires less time. That's household members with less shopping time are more inclined to e-shopping. In terms of land use, we find a V-shaped relationship between online purchases and population density. When the population density is really low, which means going to a store takes a lot of time, then as population density increases, time spent in going to store will decrease. As a result, households will be more willing to shop in stores. But as population density continues to increase, households may be more inclined to become more inclined to online shopping. This is because greater population density means greater human interactions, reducing the available time for in-store shopping. Also, people living in dense areas tend to have greater access to internet. Related to this last point, we found that households living in urban areas tend to e-shop more. The difference is even stronger in 2017. And lastly, the daily internet use has an impact on online shopping. This is the case for both 2009 and 2017, which supports the argument that more frequent use of internet enables online shopping. There could also be induced demand because of the more frequent internet use. However, probably because of the increasing popularity of internet, we find the effect of internet use is diminished somewhat in 2017. So to summarize, this study leverages recent US National Household Travel Survey data to develop a GBM model to predict household online purchases in 2009 and 2017. And this allows us to conduct national scale investigation at the household level. We use Shapley value to quantify input variable importance, and we use cumulative local effects to characterize the relationship between predicted online shopping demand and input variables. We find that the household income contributes almost always the most to predicting online shopping demands. Comparing the 2 years, the importance of internet use and gender diminishes, while household member age and household size become more important. The relationship between input and the response variables have been investigated extensively. We find the generation growing up with e-shopping significantly influences the effect of adult percentage in a household on online shopping. The household owning property tend to buy more online. Travel time has positive relationship with online purchases. Population density has a mixed effect. Living in urban areas and having daily internet use encourage e-shopping. The models developed here can be used for e-shopping related free demand generation purposes. And the models and insights can also be considered for evaluating potential impact of on e-shopping demand of relevant policies such as land use and zoning, fuel tax, transportation demand management to reduce trip learning. It can also be used for future when further releases of National Household Travel Survey data or similar data become available to gain more in-depth understanding of the evolution of the impact of these variables. And finally, the modeling and analysis could be further refined. For example, we can first classify the household locations and then perform prediction, maybe to achieve even greater prediction accuracy. So with that, I'd like to thank you for your attention and welcome your comments and discussions.
Thank you very much. It's very interesting talk. I think like in general, like identify feature importance and explain the machine learning is even more important for smart city research in general. It gives people not just what observed, but also why it happens. So yeah, I'm just wondering, like, can you talk a little bit more on the method you are using? Like, how reliable they are in terms of to determine the feature importance, or you see there's limitations or things we can still improve? Because the importance is something harder to quantify, right? Like it is the most important is only by this particular measure you're choosing.
Yeah, so the feature, I guess you're talking about feature importance. So the motivation for us to consider this called Shapley value, which is different from the kind of a state of the practice, Gini-based feature importance is we want to overcome this drawback that Gini importance tends to bias towards variables with high cardinality. So I'm not showing the detailed math here for how Shapley values actually work. But basically, it borrows the concept from game theory. So basically, we look at the different sequences of having the input variables into the prediction. And we kind of look at all the possible combinations of the sequences. And for each sequence, we look at the marginal contribution of a variable to the predicted online shopping demand. And then we take the average of over all the possible sequences. So that's kind of the idea behind the Shapley values.
So for this study, have you also compared like the importance with the feature importance result from the Shapley method versus Gini method, or other methods? Are they or
yeah, we actually initially we used the Gini importance, and then we review literature and we found that yeah, there's some drawback, but we haven't put Gini coefficient Shapley value side by side in the paper, but that certainly can be done.
Okay. Yeah, I'm mostly just wondering like what kind of metrics we can use to say this method can maybe determine it's better important than the others.
So you can just based on empirical results, you can't say which one is better, right? It's all based on kind of if you believe this theory behind the methods, and if you think that people's claim of this drawback is reasonable, and then you can claim, well, if we use this method, it will produce more credible results.
Yeah. Well, it's very interesting. So is there any question from audience?
Dr. Zhou, I have a question on the machine learning model part. So far, this one has 70% of accuracy. Yes. Have you tried other machine learning models like a deep neural network or other related method?
Yeah, thank you, Dr. Zhao, for your question. So yeah, here are the models we tried. We haven't tried deep learning models. So these are all machine learning models. So to my understanding, my student said that maybe for because we also tried this for city-specific modeling. Maybe for city-specific models, we do not have enough data if we want to train a deep learning model. So that's why we just focus on machine learning models. But among these models, as you can see, GBM performs the best and much better than regression models.
And this paper is under review on transportation research.
Yeah, so it's under revision. I think the comments are fairly easy to address. So we are actually submitting a revision for transportation, the Springer Journal Transportation.
Very nice, and we look forward to reading your publication.
Thank you. Yeah, I'll be happy to share with you once it's accepted.
Sounds good. Thank you.
Thank you.
Any other question from audience?
I have one question. Thank you, Dr. Zhou, for your great presentation. My question is, how do you see the impact of proximity to stores on online shopping demand? For example, some areas might have higher accessibility to stores or grocery stores than the others, so people may prefer to shop in person. So how do you see this?
That's a great question. Yeah. So the National Household Travel Survey does not provide the kind of proximity of store information. We can only, the immediate thing off the top of my head is population density. We can use that as kind of a proxy to stores. You have a high population density, then expectedly you will have more stores nearby. So that's what we could use, but there's no store specific information. That's too much detail. I don't think that'll be, it's very hard to publish such information for a specific household.
Thank you.
Thank you.
Okay, it seems there's no more questions from audience and we're right on time. Thank you very much for Dr. Zhou. It's a very interesting work and a very interesting talk. We are going to posting your presentations, and if you have slides, we are happy to post them online, or if you want to wait until your paper published, then we can post that one later as well. With that, and we conclude our today's meetings. And thanks for everyone to attending and listening. Hope to see you next time. Bye.
Okay, thank you everyone. Thank you very much. Bye-bye.
Thank you, Dr. Zhou. Bye.
Thank you.